The Fermi Paradox. The universe is 13.8 billion years old, and the math says it should be crawling with intelligent life. Astronomer Enrico Fermi sat down at Los Alamos in 1950 and asked one devastating question. If they exist, where are they? The numbers are brutal. Hundreds of billions of galaxies, billions of stars per galaxy, planets everywhere. Even at sublight travel speeds, a civilization could colonize the entire Milky Way in under 10 million years. That's a blink in cosmic time. So the silence isn't just strange, it's the loudest thing in physics. The pivot is this. The silence might not mean absence. It might mean we're too primitive to hear the signal, or too late, or the universe keeps resetting intelligent life before it spreads. Every solution to the Fermi paradox implies something terrifying about our own future. The twin paradox. Two twins. One stays on Earth, one boards a spacecraft and travels near the speed of light. When the traveler returns, she's younger than her sibling, not metaphorically. Physically, biologically younger. Einstein's special relativity demands it. Time dilates at high velocity. The closer you move to light speed, the slower your clock ticks relative to a stationary observer. The paradox arrives when you flip the frame. From the traveler's view, isn't it Earth that moved? Shouldn't both twins age equally? Here's where it turns. The traveler accelerates and decelerates. That asymmetry breaks the symmetry. Only one twin feels the force of the turn. The math resolves cleanly. The biology does not. This is a confirmed phenomenon. Atomic clocks on jets age slower than clocks on the ground. Time is not a constant. It is a variable that bends around speed. The grandfather paradox. You build a time machine. You travel back. You accidentally prevent your grandparents from meeting. Now you were never born. But if you were never born, you never built the machine. If you never built the machine, you never traveled back. If you never traveled back, your grandparents met, you were born. You built the machine. The loop has no exit. Physicists have spent decades trying to kill this paradox or domesticate it. Stephen Hawking proposed the chronology protection conjecture in 1992. The laws of physics conspire to prevent time travel to the past, making the universe safe for historians. Others argue for the Novikov self-consistency principle, where any action a time traveler takes was always part of the timeline. The real cost is philosophical. Either free will is an illusion inside a closed loop, or time travel is simply impossible. Neither answer is comfortable. Maxwell's demon. In 1867, James Clerk Maxwell imagined a tiny creature guarding a door between two chambers of gas. The demon watches individual molecules. Fast ones it lets through one way, slow ones the other. Over time, one chamber heats up, one cools down. Order emerges from disorder without doing work. That would violate the second law of thermodynamics, the law that says entropy always increases. The demons seemed to break physics with nothing but attention. The resolution took nearly a century. In 1961, Rolf Landauer proved the demon must store information about each molecule. When it erases that memory to reset, it releases heat. The act of forgetting costs energy. Information is physical. That single insight launched the entire field of information thermodynamics and rewired how physicists think about computation and heat. The Olbers paradox. Stand outside on a clear night. The sky is dark. That should be impossible. If the universe is infinite, ancient, and filled with stars in every direction, every line of sight should eventually hit a star. The night sky should blaze as bright as the surface of the sun. Heinrich Olbers formalized this in 1823, though others noticed it earlier. The resolution is deeply unsettling. The universe is not infinitely old. It had a beginning. Light from the most distant stars hasn't reached us yet. The universe is also expanding, stretching light toward the red end of the spectrum until it fades below visibility. The darkness of the night sky is direct observational proof of the Big Bang. Every time you look up and see black, you're seeing the echo of a beginning. Schrödinger's cat. Erwin Schrödinger built this thought experiment in 1935 specifically to mock quantum mechanics. A cat is sealed in a box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the énonciation detector triggers, the vial breaks, the cat dies. Quantum mechanics says the atom exists in superposition, both decayed and not decayed until observed. By extension, the cat is both alive and dead until you open the box. Schrödinger meant this as a reductio ad absurdum. The Copenhagen interpretation of quantum mechanics accepted it almost literally. The many worlds interpretation says both outcomes happen, splitting into parallel branches. The pivot nobody mentions. We still don't have consensus. The measurement problem, what collapses a quantum superposition and why, remains one of the deepest unsolved problems in all of physics. The bootstrap paradox. A time traveler brings Beethoven's Fifth Symphony back to 1770 and gives it to Beethoven, who publishes it as his own. The symphony exists, but who composed it? The traveler learned it from recordings of Beethoven. Beethoven learned it from the traveler. The information has no origin point. It loops forever, causeless. Physicists call this a causal loop. The object or information bootstraps itself into existence. Unlike the grandfather paradox, there's no contradiction, just a profound absence of cause. Some physicists argue this is less a paradox and more a feature of a self-consistent universe. Others find it deeply troubling. If information can exist without a source, what does that do to the concept of creation? The question has no clean answer, and that's exactly the point. Zeno's paradoxes. Around 450 BCE, the Greek philosopher Zeno of Elea proposed that motion is impossible. To cross a room, you must first cross half the room, then half of what remains, then half again. The divisions are infinite. How can you complete infinite steps in finite time? For 2,000 years, this felt like a genuine crisis. The resolution required calculus, specifically the concept of a convergent infinite series. Infinite steps can sum to a finite number. The mathematics is clean. But here's the pivot. Some physicists argue Zeno was accidentally asking something real. At the Planck length, roughly 10 to the minus 35 meters, space may not be continuously divisible. There may be a smallest possible distance. If space is quantized, Zeno's infinite divisions hit a flaw. The ancient paradox may have been pointing at quantum gravity all along, the Mpemba effect. In 1963, a Tanzanian schoolboy named Erasto Mpemba noticed that hot ice cream mix froze faster than cold mix. He told his physics teacher. The teacher dismissed him. Mpemba persisted, eventually collaborating with physicist Dennis Osborne to publish a paper in 1969. Hot water freezing faster than cold water under certain conditions became known as the Mpemba effect. The paradox is that thermodynamics seems to say this shouldn't happen. Colder water should reach freezing first. Researchers have proposed evaporation, dissolved gases, convection currents, and hydrogen bond dynamics as explanations. None fully holds. A 2016 study from Simon Fraser University suggested it may depend on the initial conditions so precisely that it isn't a universal effect at all. The paradox survives. A schoolboy's observation still doesn't have a settled answer. The EPR Paradox. In 1935, Einstein, Podolsky, and Rosen published a paper designed to prove quantum mechanics was incomplete. Two particles are entangled. Measure one and the other instantly reflects a correlated result, regardless of distance. Einstein called it spooky action at a distance and hated it. It seemed to violate relativity. Nothing should transmit information faster than light. The pivot came in 1964 when physicist John Bell devised a mathematical test. Experiments by Alain Aspect in 1982 confirmed that entanglement is real and non-local. The correlation is genuine, but here's the catch. You can't use it to send information faster than light. The results are random until you compare notes through a classical channel. Einstein was wrong about the incompleteness. The universe is genuinely strange at the quantum level, and locality is not sacred. The arrow of time paradox. Every fundamental law of physics works equally well forward and backward in time. Run a video of two billiard balls colliding and the reversed version looks just as valid. But run a video of a glass shattering and reversing it looks instantly absurd. Entropy increases. Broken things don't reassemble. The future is different from the past in every lived experience, yet the equations don't care. Which direction time flows? The paradox is that irreversibility emerges from perfectly reversible laws. The leading explanation involves the extraordinarily low entropy state of the early universe. Time's arrow is not a law. It's a consequence of a very specific initial condition. Some physicists, including Sean Carroll, argue we still don't understand why the universe started in such an improbably ordered state. The arrow of time points at an unsolved mystery at the birth of everything, the ultraviolet catastrophe. In 1900, classical physics predicted that a perfect blackbody radiator would emit infinite energy at high frequencies. Every heated object should be destroying the universe with ultraviolet radiation. Obviously, it doesn't. The prediction was so wrong it had a name, the ultraviolet catastrophe. Max Planck solved it by proposing something radical. Energy is not continuous. It comes in discrete packets, quanta. He introduced the constant now bearing his name. The equations worked. The catastrophe vanished. But Planck himself didn't fully believe his own solution. He thought it was a mathematical trick. It wasn't. That uncomfortable fix launched quantum mechanics, the most precisely tested theory in the history of science, accurate to 1 part in a trillion. A catastrophe that shouldn't exist became the doorway to the modern world. Every one of these paradoxes followed the same hidden pattern. A system that looked complete, a universe that seemed fully mapped, ran into one observation or one equation that refused to obey. The resolution never came from patching the old model. It came from breaking it entirely. The paradoxes weren't failures of physics. They were physics announcing it was ready to become something bigger. The ones still unresolved, Fermi's silence, the measurement problem, the arrow of time are not embarrassments. They are the live wires. Touch one and you might be holding the next revolution.